So hi guys, my name is Kyohei Sawada. First of all, thank you all for being here today. I'd like to thank the host and organizers for this great challenge and opportunity. And it's very honored to be part of this event. And I'm excited to share my work with you today. So today I have uh, the simple self introduction and solution summary, and I have the four key points that the crucial role in my solution. And also I have things didn't work. Okay, so let me introduce my background. I have a master's degree in mechanical engineering and worked for over 5 years as a researchers in the aerospace industry and focusing on computational fluid dynamics. Though those are the products I have engaged so far. And this airplane project is the big one, but unfortunately, this was closed. So I decided to transition into data science, leveraging my aerospace engineering background. And for the past 3 years, I have specialized in deep learning and machine learning, mainly applied in the finance industry. And along the way, I've also been actively participating in Kaggle competitions, which have played a key role in my learning and growth into data science field. Okay, let's move on to the solution summary. So here is a quick summary of my solution. I used four image models and their outputs were fed into three GBDT models. In addition, there was another GBDT model that only used the table features. I believe many participants use a similar approach based on the public notebook shared during the competition. And what's unique about this approach, my approach, is that there are two types of image models, uh, which were trained differently. This allowed for more effective integration with the GBT models to improve the overall prediction. And as for the result, my final CV score was 0.1830, and the public is 0.1355 and private 0.17229. So the CV and readable scores were pretty close, so showing that I could confirm the consistent performance. And now I will explain some key points. So in this slide, I picked up some hard samples. Take a look at this set of images. The left-hand side, the label are 0, which means non-malignant, while the right-hand side is a malignant case. So as you can see, the images look quite similar, but labels are different. The same thing here and here. So what I want to highlight is that there are many difficult samples like this, which confusing training my image models. And as part of my investigation into the features of difficult samples, I looked at the role of IDDX1 feature, and I found that when IDDX1 is labeled as indeterminate, these samples often become harder to classify. This makes sense because as indeterminate case suggests some suspicious of cancer. So now I can say that by checking the IDX1 value, it's possible to identify to some extent samples that are not malignant but visually appear to be malignant. In similar way, I also investigated the IDDX2 features, and I found that when IDDX2 is not null, the samples often become harder to classify. This also makes sense because when there is a diagnostic description in IDDX2, these cases tend to involve some suspicions of malignancy, which means the images often look visually suspicious. So based on these findings from IDDX1 and IDDX2, I decided to adjust the labels for training the image model. The, the role of the image model is to make predictions purely based on the visual characteristics of the images without being influenced by the potential misleading labels. So therefore, I believe it is necessary to adjust labels for samples that could confuse the model. So with this in mind, I trained two types of image models. One with original labels, which means the target, and another one is adjusted labels for cases where IDDX1 is indeterminate or IDDX2 has a diagnosis. This allowed the image model to focus solely on the visual features of malignancy, improving its ability to detect malignant patterns without being confused by the actual label. And finally, the ultimate classification of benign and malignant cases is handled by the GBDT model. So that is key point one, and now move on to key point two. So I'm going to explain the sampling strategy I used to address the class imbalance. Since there were more negative samples, I applied downsampling and make sure to change the negative samples in each epoch. In this approach, I expected to prevent overfitting by exposing the model to a variety of negative samples. And for the positive samples, I ensure that each batch maintained a fixed ratio of positive to negative samples. Based on my experience, I expected this would help stabilize the learning process by ensuring that both positive and negative samples were always present in the same batch. So key point three is so in this key point, I like to highlight one of the challenges in this competition. Uh, this is the evaluation score history during the training. As you can see, there is a significant variance across the folds. I believe this is due to the label imbalance in the dataset, which made it difficult to achieve stable training and consistent evaluation results. So instead of relying on the partial training or single fold evaluation, I made sure to train across all five folds and always evaluated my model based on the average over the five folds. And this helped reduce the instability and gave more reliable measures of model performance. And key point four, I tried many image models and found that smaller models performed better. Given the low image resolution in this competition, there wasn't need for large models. Smaller models were enough to get good results. This was, I think, many participants also noticed, and I observed the same in my experiment also. By using small models, I was able to reduce overfitting, which improved performance, and I also believe the approach helped align with the CV-LB scores. So now I explain the things didn't work. The number one is I noticed that the data had separate variables for left and right, and my GBDT model treated them as distinct features. And this setup seemed to suggest that there might be a difference in cancer occurrence between two sides, which didn't quite make sense to me. From medical perspective, the probability of malignancy should be even between both sides, in my opinion. So I thought it would be better to combine the left and right variables into one, hoping for also better CV score. However, when I tested this idea, the CV score actually got worse since I was relying on, because I was throughout this competition relied on my CV result. I decided not to proceed with this idea, even though I have some doubt about keeping this left-right distinction initially. And the thing didn't work number two is residual model. Here I would like to explain the idea behind the residual model. The goal was to integrate image data with GBDT model in a new way. Specifically, I used an image model to learn the residuals or the difference between the probabilities predicted by GBDT model and actual labels. The process was to first the GBDT model make predictions, then calculate the residuals between the predictions and the true labels. The image model would then run these residuals with the hope that it could capture the information that GBDT model missed. And I tested this idea, but unfortunately, the CV score got worse. And I believe the main challenge of this idea is that residuals of some samples can be explained by images, but there are also samples whose residuals and images are not relevant. So, so there could be lots of noise. So removing those noise and only focus on effective samples. And also with appropriate training setup, I believe this approach might have worked better. Okay, so that's pretty much of my presentation. So thank you.